Um, so in this question, we are actually asked to determine um, the the required area for this doubly reinforced concrete beam. So in this problem, we're actually given with the width of the beam, which is 350 mm, and the effective depth of the beam is equal to 600 mm, and the maximum moment is 1150 kilonewton meter. And we are also given with F prime C is equal to 28 megapascals, and F Y is equal to 420 megapascals, and modulus of elasticity of steel is equal to 200,000 megapascal. Um, so in this kind of problem, we are actually asked to determine the area required for this doubly reinforced concrete beam. So kung i-compare nato sa singly reinforced concrete beam, diri ara nato mabutang ato ang steel reinforcement with the effective depth of something from the extreme fiber. However, sa ato ang doubly reinforced concrete beam, naatay mabutang diri sa ato ang upper portion sa ato ang concrete beam, natin mabutang diri ang steel reinforcement. So with that, the first thing that you need to do is to determine first the area required sa ato ang sa lower portion diri sa ato ang concrete beam, kung pilay steel reinforcement required nga gi-ask nato ang ma-determine nato sa kini nga problem. So by this, by looking at the previous topic nga to ang na-discuss before, di ba, this is actually a singly reinforced concrete beam. So by that, we can actually the step-by-step process nga nato ang na-discuss sa previous lessons nato. So with that, by determining the area required for the steel reinforcement sa ato ang singly reinforced concrete beam, we need to determine first the P max. So by this P max, we're given this formula. However, this balanced steel reinforcement ratio is actually unknown. Pero natay formula nga gihatag sa ato ang balanced steel reinforcement, which is this one. We have this F prime C, and we have beta 1, or the beta, and we have the Fy, which is equal to 420 megapascal. So by substituting, we get the balanced steel reinforcement ratio is 0.0283. Now remember ha, ang ato ang value sa to ang beta is 0.85 if and only if ang ato ang value sa to ang F prime C is less than or equal to 30 megapascals according to NSCP. So the next thing that you need to do is na naman kay value sa to ang steel reinforcement ratio, pwede na rin ito siya ma-substitute diri as ito ang Pmax to get the value of our Pmax, and we get 0.02125 nga value sa to ang Pmax. Now with that, we have this formula to determine the maximum moment nga na-experience sa ato ang singly reinforced concrete beam. Let's assume sa nga singly reinforcement before ta mo-proceed sa ato ang pagkuha sa ato ang steel reinforcement sa upper portion sa atong ikaduha na to siya nga location. So let's say nga natay formula nga omega max is equal to P max is equal to Fy over F prime C. So by that, we'll get the value of omega max, or the moment that, or with that, we'll get the value of omega max is equal to 0.3187. Now, in order for you to get the maximum moment yung experience ato ang concrete beam sa ato ang singly reinforced concrete beam, we have this formula. Mu max is equal to phi times F prime C omega, the width of our concrete beam and the depth of our concrete beam, times 1 minus 0.59 times omega. So by substituting all the value, we'll get the maximum moment of 821.756 kilonewton meter. And in order for you to determine the area for the singly reinforced concrete beam, we have this formula by using the maximum steel reinforcement ratio. So we have AS, or let's say the area required for steel reinforcement 1 is equal to P max times the width of the concrete beam and the depth of the concrete beam. So by substituting all the value we get, and we get the area of 4,462.5 millimeters squared. And now, in order for you to determine the area steel from the compression phase, we have this formula. So moment is equal to phi times tension 2 times d minus d1. Now, what is this d prime? I mean, what is this d prime? Now, d prime is actually distance imuhang steel reinforcement from the extreme fiber of the concrete beam. Now, since we don't have this moment nga experience sa ato ang compression phase, so we have this formula to get that one. So mn2 is equal to, we are actually given this, the maximum moment nga na experience sa atong concrete beam, which is actually equal to 1,150 kilonewton meter, and this mu max nga experience sa ato ang kato sa singly reinforced concrete beam, we have 821.756 kilonewton meter. So by that, we'll get the area the moment experience in the compression phase is equal to 328.244 kilonewton meter. So by substituting all the given values to get the area for the AS2, or for the area still required for sa compression phase na to, we have 1,618.47 mm squared. So by that, we get the total area AS1 is equal total area is equal to AS1 plus AS2 is just equal to 6,080.97 mm squared. Question number 2, a rectangular beam with a simple span of 6 meter supports a dead load of 17.50 kilonewton per meter and a live load of 36.5 kilonewton per meter. For architectural reasons, the cross-section is limited to 300 mm width and a total depth of 540 mm, with an effective depth of 460 mm, and then the dead load includes the weight of the beam. So if F prime C is equal to 20.68 megapascals and Fy is equal to 275.8 megapascals, we are actually asked to determine the factored uniform load and the steel area required for compression and the steel area required for tension. Now, in order for you to determine the factored uniform load, we have this formula. And since the weight of the dead load, since the dead load actually includes the weight of the beam, so we don't have to calculate na sa ato ang weight sa ato ang beam itself. So with that, let's just substitute. So omega u is equal to 1.4 times the dead load times plus 1.7 times the live load. So we get 86.55 kilonewton per meter. And in this kind of problem, let's determine first the steel area required for tension before we proceed to decompression. And for the steel area required for tension, we are actually just the same with the question number 1. Let's start first in singly reinforced concrete beam by using the P max value. So with this, we'll get the value of P max is equal to 0.75 times the balanced steel reinforcement ratio. Since we don't have this value, we have this formula, and let's substitute all the given values. We get the steel reinforcement balance. The balanced steel reinforcement ratio is equal to 0.037123. And by substituting this value, we get the value of P max is equal to 0.02784. And by using this formula, we get the area still required for tension is equal to P max times the width of the beam times the effective depth of the beam. So we get the value of area still required for this tension is equal to 3,841.92 millimeters squared. In this problem, we are actually asked to determine the steel area required for the compression. So with that, we'll determine first the value of MD. and the value of mu to compare whether this kind of problem should be designed as doubly reinforced concrete beam or not. So if dako ang value sa to ang MD, this should not be designed as doubly reinforced concrete beam. Otherwise, kung gamay siya, i-design na to siya as doubly reinforced concrete beam. So let's start. In order for you to get the value of MD, we should determine first the value of RA, which is actually the depth of the rectangular stress block. So with that, we have the formula of A is equal to area steel sa to ang nakuha sa to ang tension times your Fy over beta 1 times F prime C times the depth of the concrete, not the depth but the width of the concrete beam. So by substituting all the given values, we'll get the depth of this rectangular stress block is equal to 200.93 mm. So by this formula, we are able to get the value of our MD, the moment times the reduction factor. So Mn is equal to As times Fy times the effective depth of the concrete beam minus A over 2. So by substituting, we'll get the value of 380.96 kilonewton meter. So by that, we'll just need to multiply this moment by the reduction factor, and according to NSCP, the value of reduction factor, or in phi symbol, is equal to 0.9. So by multiplying that number to this value, we get the value of 342.88 kilonewton meter. And to get the maximum moment in experience sa to ang concrete beam, we have this formula. Mu is equal to omega u times the span of our concrete beam, which is just equal to L. And by substituting all the given values, we'll get the value of maximum moment sa to ang concrete beam is equal to 389.475 kilonewton meter. And now, since our MD is less than to MU, so therefore this beam should be designed as doubly reinforced concrete beam. Now, in order for you to compute the area required for the compression, let's assume that F prime S is equal to Fy. That means nga ang ato ang compression steel nag-yield siya to make our design safe. So first, let's find the value of our D prime, which is just equal to 40 minus, the 40 is actually the covering o sa to ang stirrups, minus the 10 mm. Let's assume nga 10 mm ang diameter sa to ang stirrups, and for the longitudinal bar is 22 mm. And we'll get the value of the distance of D prime is equal to 61 mm. So this is actually the distance of the steel reinforcement from the extreme fiber of the concrete beam. So we have that value. We have to determine the excess moment can experience sa ato ang compression steel. So we have the formula M1 is equal to maximum moment divided by the reduction factor minus MD. So we get the value of M1 is equal to 93.144 kilonewton meter. And to get the area of the area steel required for the compression is just equal to A prime S, which is the area for the compression. The area steel for the compression is equal to M1 over Fy times the effective depth of our concrete beam sa katong singly reinforced concrete beam minus the D prime sa, which means nga nakuha na to which is 61 mm. So by substituting, we get the value of 846.424 mm squared. That's it.